Hello there and welcome to Zero Drift, your peaceful passage through the universe. Tonight, we are going to explore one of the most extraordinary stories in the history of physics. A story that begins with a question so fundamental it sounds almost philosophical: where does mass come from? And ends in a moment of collective human triumph, when the largest scientific machine ever built confirmed the existence of something that had been predicted half a century earlier, hidden in the invisible fabric of space itself. This is the story of the Higgs boson and the Higgs mechanism. It is the story of a field, an invisible, all-pervading quantum field that fills every cubic millimeter of space, that has been present since the earliest moments after the Big Bang, that you are passing through right now as you lie still and breathe, and of what happens when that field settles into a non-zero resting value that gives mass to the particles that interact with it. It is the story of why electrons have the mass they do, why they are not massless like photons zipping through space at the speed of light, but instead have a specific, definite mass that allows them to be captured into atoms, to participate in chemical bonding, to make chemistry and life possible. It is the story of why the W and Z bosons, the carriers of the weak nuclear force, are heavy, massive particles, while the photon that carries the electromagnetic force is massless. And it is the story of the Mexican hat potential, one of the most beautiful and consequential shapes in all of theoretical physics, a potential function whose valleys, lying away from the origin rather than at it, force the Higgs field to settle into a non-zero resting value, and in doing so give mass to the particles of the Standard Model. It is the story of July 4, 2012, when two vast experimental collaborations at CERN's Large Hadron Collider, the ATLAS and CMS experiments, announced simultaneously that they had observed a new particle consistent with the long-predicted Higgs boson at a mass of approximately 125 gigaelectron-volts. The announcement was made in an auditorium packed with physicists, with Peter Higgs himself in the audience, who was seen wiping tears from his eyes. Nobel Prizes were awarded the following year to Higgs and his collaborator Francois Inglet. The story of the Higgs is one of the most beautiful in physics. It involves abstract mathematics, quantum field theory, the calculus of potentials, the quantization of field ripples, applied to describe something entirely invisible and yet entirely real. It is a story about the deep structure of the universe, about how mass emerges not as a fundamental property of particles, but as a consequence of how those particles interact with a background field that permeates all of space. So settle in, let your body grow heavy and still. Let your breathing find its own slow rhythm, and allow the story of the Higgs boson, of the field that fills all space and gives particles their mass, to carry you gently towards sleep. To understand the Higgs mechanism, we need to begin with the concept of a quantum field. Not in an abstract or metaphorical sense, but in the precise sense that modern physics uses the term. In quantum field theory, the fundamental entities are not particles, but fields, mathematical objects that take on a value at every point in space and time. The electromagnetic field has a value, a combination of electric and magnetic field strengths, at every point in space, at every moment in time. The electron field has a value at every point. The quark fields have values at every point, and the Higgs field has a value at every point. Particles, in quantum field theory, are not independent objects that live in a field-free void. They are excitations of the fields, ripples, disturbances, vibrations in the underlying fields. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. A Higgs boson is a ripple in the Higgs field. The field is primary. The particle is the field's way of manifesting as a localized, discrete quantum of energy. This picture, fields as primary, particles as excitations, is one of the deepest conceptual shifts in the history of physics. It replaced the earlier picture of point particles interacting through forces, and it resolved many of the paradoxes and infinities that had plagued earlier attempts to combine quantum mechanics with special relativity. Quantum field theory is our most successful and most precisely tested theory of nature, with predictions confirmed to better than 1 part in a billion in the case of the electron's magnetic moment. Now, within quantum field theory, there are 2 basic types of particle, massless and massive. A massless particle, like the photon, obeys a wave equation with a specific form. When you take a traveling wave solution and substitute it into the wave equation, you get a relationship between the frequency of the wave and its wave number, the dispersion relation, that says the frequency is simply proportional to the wave number, with the speed of light as the proportionality constant. As the wave number approaches 0, as the wavelength becomes very long, the frequency also approaches 0. There is no minimum frequency. The particle can have arbitrarily low energy. A massive particle obeys a modified wave equation, 1 with an additional restoring term. When you substitute a traveling wave into this modified equation, you get a modified dispersion relation that includes a minimum frequency. Even as the wave number goes to 0, the frequency does not go to 0, it goes to a minimum value. This minimum frequency corresponds, through the quantum mechanical relation E equals h bar omega, to a minimum energy, the rest mass energy of the particle. The particle cannot have less energy than this, even when it is at rest. It is this minimum energy that we identify as the mass of the particle. The mass of a particle, in this picture, is determined by the minimum frequency of the corresponding field ripple, and the minimum frequency is determined by the restoring term in the wave equation. And the restoring term comes from the shape of the potential function associated with the field. This is the key chain of ideas that leads to the Higgs mechanism. The mass of a particle comes from the shape of the potential that governs its field, and the Higgs mechanism is a specific way in which an ordinary massless field can acquire an effective mass by interacting with another field, the Higgs field, that has settled into a non-zero resting value. Drift a little deeper now. The room is quiet, the night is holding you, and the story moves into the mathematics of potentials, the mathematical functions that determine where a field rests and what the ripples around that resting point look like. Every physical system tends to settle into its lowest energy configuration. A ball placed anywhere on a hilly landscape will roll down to the lowest valley and stay there, unless disturbed by some external force. A spring stretched from its natural length will contract until it returns to equilibrium. A field, in quantum field theory, behaves similarly. It tends to settle into the configuration that minimizes its potential energy. For a simple quadratic potential, a potential that looks like the letter U, with a single minimum at 0, the field rests at 0. This is the most familiar case. The field has a definite equilibrium value of 0, and small disturbances away from 0 are the field ripples that become particles. The mass of the particles is determined by the curvature of the potential at 0, how sharply the potential curves upward near the minimum. But what if the potential had a different shape? What if, instead of curving upward from 0, the potential curved downward at 0, creating an unstable equilibrium there, with 2 stable minima lying on either side at some non-zero value? Then the field would not rest at 0. It would roll off the unstable hilltop at 0 and settle into one of the 2 valleys at a non-zero resting value. This is exactly the shape of the Mexican hat potential, the name given to a particular potential function that plays a central role in the Higgs mechanism. The Mexican hat potential has a local maximum at the origin, at the value 0 of the field, and 2 symmetric minima lying away from the origin, at field values of plus and minus some characteristic value that depends on the parameters of the potential. The name comes from the shape of a 2-dimensional generalization of this potential, which looks like the crown of a Mexican sombrero, a central peak surrounded by a circular valley. In the 1-dimensional version that we will use, it looks like a double well, 2 valleys with a hill between them. The The crucial feature of the Mexican hat potential is that the field's true resting state lies away from zero. The field does not want to be zero. Any field starting near zero will roll off the central hill and settle into one of the two valleys at a non-zero value. This non-zero resting value is the background value of the field, the constant, space-filling, all-pervading value that the field takes on everywhere, not as a ripple or an excitation, but as a permanent background condition. And this background value is the key to the Higgs mechanism. Let the story settle gently as we follow the mathematics to its beautiful conclusion. The Higgs mechanism, the process by which particles acquire mass, works as follows. Consider two fields. The first field, call it phi, has a Mexican hat potential, which forces it to settle into a non-zero resting value. The second field, call it chi, is initially massless, with a wave equation that contains no restoring term and therefore no mass. Now let the two fields interact with each other through a simple coupling term in their potential. The coupling term is proportional to the product of the squares of the two fields, phi squared times chi squared, multiplied by a coupling constant that sets the strength of the interaction. When phi settles into its non-zero resting value, something remarkable happens to the equation of motion for chi. The interaction term, which contains phi squared, becomes a constant, the square of the resting value of phi multiplied by chi squared. This constant plays the role of a restoring term in chi's wave equation. It gives chi a minimum frequency. And that minimum frequency corresponds to a mass. The mass of the chi particle is proportional to the coupling constant times the resting value of phi. It is not a mass that was put in by hand. It was not declared at the beginning. It emerged, automatically, necessarily, as a mathematical consequence of phi settling into its non-zero resting value and the two fields being coupled to each other. This is the Higgs mechanism in its simplest form. A field with a Mexican hat potential settles into a non-zero resting value. Other fields that interact with it acquire a mass from this non-zero background. The mass is determined by the coupling strength and the resting value of the Higgs-like field. In the real universe, the Higgs field plays the role of phi. The W and Z bosons and the quarks and leptons of the Standard Model play the role of chi. They begin, in the symmetric version of the theory, as massless fields. The Higgs field settles into its non-zero resting value, which has been precisely measured, through indirect means, to be approximately 246 gigaelectronvolts. And through their couplings to the Higgs field, the W and Z bosons, the quarks, the electrons, the muons and taus, all the massive particles of the Standard Model, acquire their masses. The photon, which does not couple to the Higgs field in the same way, remains massless. The gluons, which carry the strong nuclear force, also remain massless. And the Higgs boson itself, the ripple in the Higgs field around its resting value, has a mass determined by the curvature of the Mexican hat potential at its minimum, which was measured at the LHC to be approximately 125 gigaelectronvolts. As you rest in the deepening quiet of this night, let the full significance of what we have described settle in. The mass of every massive particle in the universe, the mass of the electron in every atom of your body, the mass of the quarks inside every proton and neutron in every nucleus, the mass of the W boson that mediates the radioactive decay of neutrons, all of this mass comes from the same source. It comes from the interaction of those particles with the Higgs field, a field that permeates all of space with a constant non-zero background value. You are not merely in the Higgs field, you are passing through it with every breath. Every electron in your body is interacting with the Higgs field right now, and it is this interaction that gives those electrons their mass, that allows them to be bound in atoms rather than zipping away at the speed of light, that makes chemistry and biology and life possible. If the Higgs field was suddenly switched off, if some hypothetical cosmic switch could set its background value to zero, the electrons in your body would instantly become massless. They would immediately begin moving at the speed of light. They could no longer be bound in atoms. atoms in your body would dissolve. Every proton and neutron, which get most of their mass from quantum chromodynamics rather than the Higgs field directly, would still exist, but the electrons that orbited them and the quarks whose masses come partly from the Higgs would behave entirely differently. Chemistry would be impossible. No molecules, no life, no you, no me, no anything with the structure that the universe currently has. The Higgs field is not merely a detail of particle physics. It is a precondition for the existence of everything we know. The history of the Higgs mechanism is a story of theoretical physics at its most ambitious, of physicists following the mathematics to counterintuitive conclusions and trusting the equations even when the physical picture seemed strange. The problem that the Higgs mechanism was invented to solve was a problem of symmetry and mass. In the 1960s, physicists were developing the theory of the weak nuclear force, the force responsible for certain types of radioactive decay, for the process by which a neutron can convert into a proton by emitting an electron and an antineutrino. The weak force is mediated by particles, the W boson and the Z boson, just as the electromagnetic force is mediated by the photon. But there was a profound asymmetry between the weak force and electromagnetism. The photon is massless. The W and Z bosons are very massive, roughly 80 to 90 times the mass of a proton. This mass difference has dramatic consequences for the behavior of the forces. The photon, being massless, gives rise to a long-range force. The electromagnetic force extends over arbitrarily large distances, falling off as the inverse square of the distance. The massive W and Z bosons give rise to a short-range force. The weak force operates only over distances smaller than the size of a proton, roughly 10 to the negative 18 meters. Theorists in the 1960s were trying to unify the electromagnetic and weak forces into a single theoretical framework, what would eventually become the electroweak theory, unified by Sheldon Glashow, Abdus Salam, and Steven Weinberg, who shared the Nobel Prize for it in 1979. But the unification seemed to require that the W and Z bosons be massless, like the photon. The symmetry of the unified theory required it. And yet the W and Z bosons were demonstrably massive. The short range of the weak force proved it even before they were directly detected. The resolution was the Higgs mechanism. The W and Z bosons start out massless in the symmetric version of the electroweak theory. The Higgs field then settles into its non-zero resting value, breaking the symmetry of the theory, a process called spontaneous symmetry breaking. And through their couplings to the Higgs field, the W and Z bosons acquire their masses. The photon, which couples to the Higgs field differently, remains massless. This resolution, the Higgs mechanism, was proposed independently by several physicists in 1964. Peter Higgs in Edinburgh, Francois Inglet and Robert Brout in Brussels, and Gerald Guralnick, Carl Hagen, and Tom Kibble in London. Each group wrote papers pointing out that certain quantum fields could acquire mass through spontaneous symmetry breaking, in a way that was consistent with the mathematical requirements of gauge theory. Peter Higgs was the one who explicitly pointed out that the mechanism would predict a new massive scalar particle, what would later be called the Higgs boson. This prediction was the key observational signature of the mechanism, the particle that could be searched for at high-energy accelerators and whose discovery would confirm that the mechanism was real. The search took nearly 50 years. Let your eyelids grow heavier as the story moves to the machine that found the Higgs, the Large Hadron Collider at CERN, and the human effort that built it. CERN, the European Organization for Nuclear Research, is located near Geneva, on the border of France and Switzerland. It was founded in 1954, in the years following the Second World War, as a joint European scientific enterprise, a way of pooling the resources and expertise of European nations for fundamental research in physics. It has grown over the decades into the largest particle physics laboratory in the world, employing thousands of scientists from countries around the globe. The Large Hadron Collider is the most powerful particle accelerator ever built. It occupies a circular tunnel 27 kilometers in circumference, buried approximately 100 meters underground in the countryside near Geneva. Inside the tunnel, two beams of protons travel in opposite directions, accelerated to within a few meters per second of the speed of light by a series of superconducting magnets and radio frequency cavities. Where the two beams meet, at 4 points around the ring, they are focused and made to collide, with a combined collision energy of up to 14 tera-electron-volts. The energy in these collisions is sufficient to create particles far more massive than anything that exists in ordinary matter. When two protons collide at these energies, the quarks and gluons inside them can interact, exchanging enormous amounts of energy in a brief fraction of a second. From the energy of this interaction, new particles can be created through the equivalence of mass and energy expressed in Einstein's famous equation. If the collision energy is greater than the rest mass energy of a particle, that particle can be created from the collision. The Higgs boson, at a mass of 125 giga-electron-volts, requires collisions at energies well within the reach of the LHC. But creating a Higgs boson is only the beginning of the challenge. The Higgs boson, once created, decays almost immediately within roughly 10 to the negative 22 seconds into other, lighter particles. It cannot be detected directly. It must be inferred from the decay products. Two enormous detector systems, ATLAS and CMS, surround two of the collision points of the LHC. Each detector is a technological marvel, layers of sensing equipment that track the trajectories and energies of every particle emerging from a collision, measuring hundreds of millions of collisions per second and identifying those rare events, 1 in billions, that might contain a Higgs boson decay. The discovery required not just the machine and the detectors, but an enormous international collaboration of physicists, thousands of scientists from dozens of countries, working for decades to design, build, calibrate, and operate the LHC and its detectors, to develop the theoretical predictions for how the Higgs boson would appear in the data, and to analyze the petabytes of data that poured from the detectors. When the signal was found, a small but statistically significant excess of events in certain decay channels, at a mass of approximately 125 giga-electron-volts. It was confirmed by both ATLAS and CMS independently, each analyzing their data with different methods, each finding the same signal. The probability that the excess was a statistical fluctuation rather than a real particle was less than 1 in 3.5 million, the 5 sigma threshold that particle physicists require before claiming a discovery. On July 4, 2012, the results were announced to a packed auditorium at CERN. The applause was sustained. Peter Higgs, then 83 years old, sat in the audience and wept. The discovery of the Higgs boson was described, at the time, as the discovery of the century. Some went further and called the Higgs the God particle, a name that Higgs himself found embarrassing and that most physicists find misleading. The nickname came from a book by Leon Lederman, a Nobel Prize-winning physicist who had actually wanted to call it the Goddamn particle, reflecting the decades of frustration involved in searching for it, but was overruled by his publisher. The name God particle stuck in the popular imagination, partly because it evokes the central importance of the Higgs, the particle whose existence confirms the mechanism that gives all other particles their mass. But it is misleading because it suggests the Higgs boson is uniquely fundamental in a way that other particles are not, which is not true. The Higgs boson is a particle like any other particle, a quantum of a field, subject to the same mathematical framework as all the other particles of the Standard Model. It is important, but not miraculous. What is more remarkable than the particle itself is the mechanism it represents. The fact that the universe contains an invisible field that permeates all space with a non-zero background value, and that this field, through its interactions with other fields, is responsible for the masses of the elementary particles. This is a genuinely extraordinary feature of the physical world, and its confirmation by the LHC discovery is one of the great triumphs of theoretical physics. The Nobel Prize for Physics in 2013 was awarded to Peter Higgs and Francois Inglet, the two surviving proposers of the mechanism from the original 1964 papers. Robert Brout, who had co-authored the Brussels paper with Inglet, had died in 2011, a year before the discovery. Nobel Prizes are not awarded posthumously. The Higgs mechanism is not the only source of mass in the universe. It is important to understand what it does and what it does not do. The Higgs mechanism directly gives mass to the fundamental fermions of the Standard Model, the quarks and leptons, and to the W and Z bosons. The masses of these particles are proportional to their coupling constants with the Higgs field. The top quark, which has the largest coupling, is the heaviest quark, with a mass of about 173 gigaelectronvolts, more massive than a tungsten atom. The electron, with a much smaller coupling, has a mass of just 511 megaelectronvolts. The neutrinos in the minimal Standard Model have zero coupling and are therefore massless, though oscillation experiments have established that neutrinos do have small masses, implying either a non-minimal Higgs mechanism or some other source of neutrino mass. The photon and the gluon, the carriers of the electromagnetic and strong forces respectively, do not couple to the Higgs field in a way that gives them mass. They remain massless. Their masslessness is protected by the gauge symmetries of the Standard Model mathematical symmetries that prohibit mass terms for these particles. But here is a striking fact. Most of the mass in ordinary matter, the mass of protons and neutrons, and therefore the mass of atomic nuclei, does not come from the Higgs mechanism. A proton has a mass of about 938 megaelectronvolts. The three quarks inside it, two up quarks and one down quark, have masses of about 23 and 48 megaelectronvolts respectively, for a total of about 94 megaelectronvolts. The quark masses come from the Higgs mechanism. But where does the remaining 929 megaelectronvolts of proton mass come from? It comes from the strong nuclear force, from the binding energy of the quarks and gluons inside the proton, as described by quantum chromodynamics. The proton is not simply a static bag of three quarks. It is a seething sea of quarks, antiquarks, and gluons interacting through the strong force at enormous energies. The energy of these interactions, the kinetic energy of the quarks, the energy stored in the gluon fields, contributes to the mass of the proton through Einstein's equivalence of mass and energy. Most of the mass of ordinary matter comes not from the Higgs mechanism, but from the binding energy of quantum chromodynamics. This distinction is often lost in popular accounts. The Higgs mechanism gives mass to the elementary particles, the quarks and leptons. But the mass of composite particles like protons and neutrons, and therefore the mass of most of the matter we encounter, comes primarily from the strong force. The Higgs mechanism is essential, but it is not the only source of mass in the universe. The Standard Model of particle physics, of which the Higgs mechanism is a part, is the most successful quantitative theory in the history of science. It describes all the fundamental particles known, quarks, leptons, gauge bosons, and the Higgs, and their interactions through three of the four fundamental forces, the electromagnetic, weak, and strong nuclear forces. Its predictions have been verified to extraordinary precision in experiments at accelerators around the world. And yet the Standard Model is known to be incomplete. It does not include gravity. General relativity describes gravity perfectly well at the scales currently accessible to experiment, but it is not incorporated into the Standard Model framework. It does not explain the dark matter that makes up about 27% of the energy density of the universe, the invisible matter whose gravitational effects are observed in galaxies and galaxy clusters, but which does not correspond to any particle in the Standard Model. It does not explain the dark energy that is driving the accelerating expansion of the universe. and it does not explain why there is more matter than antimatter in the universe, why the Big Bang produced a slight excess of particles over antiparticles that led to the matter-dominated universe we inhabit. These gaps are not failures of the Standard Model within its domain. Within its domain, the Standard Model is extraordinarily successful. The gaps are pointers toward physics beyond the Standard Model, toward a deeper theory that includes the Standard Model as a limiting case, but goes further, explaining dark matter, unifying the forces including gravity, and resolving the matter-antimatter asymmetry. The search for this deeper theory is the central challenge of fundamental physics today. Many candidate theories have been proposed: supersymmetry, which postulates a symmetry between fermions and bosons and predicts a rich spectrum of new particles; extra dimensions, which postulate that spacetime has more than 4 dimensions at small scales; string theory, which postulates that the fundamental objects of nature are one-dimensional strings rather than point particles. None of these has yet been confirmed experimentally. The LHC continues to operate, searching for signs of physics beyond the Standard Model in the high-energy collisions of protons. So far, no clear signal has emerged. The new particles predicted by supersymmetry and other extensions of the Standard Model have not been found at the energies the LHC can reach. But the search continues, and future accelerators, more powerful than the LHC, with energies that will probe still smaller scales and higher masses, are being planned. The Higgs Boson, discovered in 2012, confirmed the last missing piece of the Standard Model, but its discovery was not the end of the story. It was a beginning, the beginning of the precision measurement of the Higgs sector, the exploration of the Higgs potential, the search for deviations from Standard Model predictions that might point toward the deeper theory. Among the deepest questions raised by the Higgs mechanism is the question of why the Higgs field has the background value it does, why it is 246 gigaelectronvolts rather than some other value. The background value of the Higgs field determines the masses of all the elementary particles that couple to it. If the background value were different, larger or smaller, the masses of the W and Z bosons, the quarks, the leptons, would all be different. The chemistry of atoms would be different. The properties of nuclear reactions in stars would be different. The conditions for the emergence of life might or might not be met. In this sense, the background value of the Higgs field is a parameter of the universe, a number that characterizes the physical world we live in. And like all the parameters of the Standard Model, the masses of the quarks, the coupling constants of the forces, the mixing angles of the CKM and PMNS matrices, it is a number that physics can measure but currently cannot predict from first principles. Why is the Higgs field background value what it is? Why is the universe the way it is, rather than some other way? These questions lie at the boundary of physics and philosophy, in the territory of what some physicists call the fine-tuning problem. The Higgs mass, in particular, seems finely tuned in a specific technical sense. In the Standard Model, without additional physics, the Higgs mass receives enormous quantum corrections from virtual particles, corrections that would naturally push it to the Planck scale, 17 orders of magnitude larger than its observed value, unless the corrections cancel with extraordinary precision. This fine-tuning is considered by many physicists to be evidence that the Standard Model must be supplemented by additional physics that protects the Higgs mass from these large corrections. Supersymmetry provides such a protection mechanism through the cancellation of corrections from bosons and fermions. Other mechanisms have also been proposed. The absence of such new physics at the LHC has deepened the puzzle rather than resolving it. The Higgs boson, in this sense, is not merely the completion of the Standard Model. It is a question mark, a place where the Standard Model points beyond itself, where the fine-tuning of its parameters demands an explanation that the theory itself cannot provide. The life of Peter Higgs is, in many ways, a story about patience and about the long arc between theoretical prediction and experimental confirmation, a story that is characteristic of the best of science. Peter Higgs was born in Newcastle upon Tyne, England, in 1929. He studied physics at King's College London and completed his doctorate in 1954. He spent most of his academic career at the University of Edinburgh, where he became a professor and where he did the work that would eventually bring him the Nobel Prize. In 1964, Higgs was 35 years old and had published relatively little of note. He was aware of a theoretical problem in the emerging theory of the weak nuclear force, the problem of how to give mass to the force-carrying particles without destroying the mathematical consistency of the theory. He read a paper by Philip Anderson, an American condensed matter physicist, who had pointed out that in superconductors, a related mechanism gave effective mass to photons inside the superconductor. Higgs was struck by the relevance of this idea to the problem in particle physics. He wrote 2 papers in rapid succession. The first was rejected by the journal Physics Letters. Higgs added a final paragraph pointing out that the mechanism he was proposing would predict a new massive scalar particle, the particle that would later be called the Higgs boson. The second version of the paper was published in Physical Review Letters. Higgs did not immediately become famous. The theoretical community was initially more interested in the mechanism than in the predicted particle. The particle was seen as a consequence of the mechanism rather than the central result. It was only gradually, as the electroweak theory of Glashow, Salam, and Weinberg was developed and confirmed, that the importance of the Higgs particle became clear. And it was only when the LHC was being designed, in the 1980s and 1990s, that the search for the Higgs boson became one of the central goals of experimental particle physics. Higgs himself lived quietly in Edinburgh throughout this period. He was not a prolific writer. After the flurry of activity in 1964, he published relatively little. He was known to his colleagues as a thoughtful, modest, and meticulous person, deeply committed to understanding and teaching physics, unpretentious about his own contribution despite its importance. He lived to see the discovery. He was in the auditorium at CERN on July 4, 2012, when the announcement was made. He was 83 years old. He received the Nobel Prize the following year, in 2013, at the age of 84. In an interview after the discovery, Higgs said that he had not expected to see it in his lifetime. He had known that the search could take decades and was genuinely uncertain whether the LHC would find the particle or whether its mass would prove to be beyond the accelerator's reach. The confirmation was, for him, a moment of profound relief, as much as of joy relief, that the prediction he had made 50 years earlier had been correct, that the mechanism was real. Higgs died in April 2024 at the age of 94. He is remembered as one of the great theoretical physicists of the 20th century, not for the volume of his output, but for the depth of a single insight that changed our understanding of how the universe gives mass to the particles that constitute it. The story of the LHC is a story of international scientific collaboration on a scale that has few precedents in human history. The machine itself is a remarkable engineering achievement. 2 beams of protons, each about the width of a human hair, circulating in opposite directions around a 27-kilometer ring, guided by approximately 9,000 superconducting magnets cooled to a temperature lower than the cosmic microwave background radiation, lower than anywhere naturally occurring in the observable universe. The superconducting magnets are cooled with liquid helium to a temperature of approximately 1.9 Kelvin, about -271 degrees Celsius. At this temperature, the niobium-titanium alloy in the magnet coils becomes superconducting, allowing enormous electrical currents to flow without any resistance, generating the powerful magnetic fields needed to bend the proton beams around the ring. Maintaining these temperatures requires one of the largest cryogenic systems in the world. The construction of the LHC took approximately 20 years from concept to first collisions, with thousands of engineers, physicists, and technicians from around the world contributing to the design and construction of the accelerator and its detectors. The total cost was approximately 4 billion Swiss francs, about $4.5 billion at the exchange rate when the machine was built. This is a large sum, but it should be set against the context of what was bought, the most complex scientific instrument ever built, capable of probing the structure of matter at distances smaller than 1/10,000th of the size of a proton. The two main experiments, ATLAS and CMS, are themselves extraordinary machines. ATLAS is the larger of the two, measuring approximately 46 meters in length and 25 meters in height, and weighing about 7,000 tons. CMS is smaller but denser, measuring 21 meters in length and 15 meters in height, and weighing about 14,000 tons. Each detector consists of layers of different sensing technologies, tracking systems to follow the trajectories of charged particles, electromagnetic calorimeters to measure the energies of electrons and photons, hadronic calorimeters to measure the energies of protons and other hadrons, muon systems to detect the penetrating muons that pass through the inner detector. The data processing challenge is immense. When two beams of protons collide, the collision produces an enormous number of secondary particles, showers of hadrons, photons, leptons, that must be tracked and measured by the detector within nanoseconds of the collision. The LHC produces approximately 40 million bunch crossings per second, each producing multiple proton-proton collisions. The raw data rate is so high that most events must be discarded in real time before they can be recorded. Online trigger systems, specialized computing hardware and software, evaluate each collision in real time and decide within microseconds whether to keep the event for further analysis. Only about 1 in a million events is retained. The rest are discarded. The events that are retained are stored and processed by a global computing grid, a distributed computing network linking facilities at universities and research institutes around the world. The LHC generates approximately 15 petabytes of data per year, 15 million gigabytes. Analyzing this data, searching for the rare signals of new particles hidden in the overwhelming background of ordinary hadronic events, is one of the most computationally intensive scientific endeavors in history. The discovery of the Higgs boson required the analysis of millions of collision events, the identification of specific decay patterns consistent with the Higgs decaying into pairs of photons or pairs of Z bosons, the careful estimation of the backgrounds from other processes that could mimic these signals, and the statistical comparison of the observed event rates with theoretical predictions. The analysis was done independently by hundreds of physicists using different methods and different software, checking and rechecking the results before the announcement was made. The fact that two independent experiments, ATLAS and CMS, both found the same signal at the same mass with the same statistical significance, using different detector technologies and independent analysis teams, provided powerful confirmation that the signal was real. The probability that both experiments would independently see a 5 sigma fluctuation at the same mass point, if there were no real particle, is vanishingly small. The Higgs boson discovery confirmed the standard model, but it also opened a new chapter in the experimental program, the detailed study of the Higgs boson's properties. The standard model makes precise predictions for how the Higgs boson decays, what fraction of the time it decays into pairs of photons, into pairs of W bosons, into pairs of Z bosons, into pairs of B quarks, into pairs of tau leptons, and into other final states. It predicts the coupling of the Higgs to each of these particles, how strongly the Higgs interacts with each one, and the couplings are all determined by the masses of the particles and the known structure of the electroweak theory. Measuring these couplings precisely and comparing them with the standard model predictions is one of the main goals of the ongoing LHC physics program. Any deviation from the standard model predictions would be evidence of new physics, of particles or interactions beyond the standard model that affect the Higgs sector. So far, the measured couplings are consistent with the standard model predictions within the experimental uncertainties. The Higgs boson decays in the way the standard model says it should. Its couplings to the W and Z bosons, to the top quark, to the B quark and the tau lepton, all agree with predictions. There is no significant deviation. This is both reassuring and somewhat frustrating. Reassuring because it confirms that the standard model, even in the Higgs sector, is correct to the precision currently achievable. Frustrating because the absence of deviations means no clear pointer toward what lies beyond the standard model. The search for deviations will continue with future data from the LHC and with future accelerators. The high-luminosity LHC, an upgrade of the current machine planned for the late 2020s, will deliver roughly 10 times more collisions than the current machine, dramatically improving the precision of Higgs coupling measurements. And proposed future circular colliders, the Future Circular Collider at CERN or the Circular Electron-Positron Collider in China, would produce millions of Higgs bosons at electron-positron colliders, allowing even more precise measurements of Higgs properties. These future measurements may reveal deviations, small but significant departures from standard model predictions that point toward the deeper theory, or they may continue to confirm the standard model with ever-increasing precision, narrowing the space available for new physics and posing an ever-sharper challenge to theorists. Either way, the Higgs boson remains at the center of the program. It is, for now, our only direct experimental access to the Higgs field, to the invisible background that permeates all of space and gives particles their mass. And the precision with which we can measure its properties is the precision with which we can probe the shape of the Mexican hat potential, the curvature of the Higgs field's potential energy landscape, the fundamental parameter of the universe that determines the masses of the particles from which everything is made. There is a profound connection between the Higgs mechanism and the concept of spontaneous symmetry breaking, a concept that appears throughout physics, from the formation of crystals to the magnetization of iron, and that is one of the most beautiful and most general ideas in theoretical physics. Spontaneous symmetry breaking occurs when a physical system has a symmetry, a transformation that leaves the laws governing the system unchanged, but settles into a state that does not respect that symmetry. The laws are symmetric, but the actual state of the system is not. A simple example is a ferromagnet, a piece of iron or another magnetic material below a critical temperature called the Curie temperature. The laws of physics governing the electrons in the iron are rotationally symmetric. They do not prefer any particular direction in space, but below the Curie temperature, the iron spontaneously develops a net magnetization, pointing in some specific direction. The symmetry of the laws is not broken, the equations are still rotationally symmetric, but the specific state of the iron is not rotationally symmetric. It points in one direction. The symmetry is broken spontaneously by the system choosing a specific state from among many equally good options. This is exactly what happens with the Higgs field. The equations governing the Higgs field, the Higgs potential, are symmetric in a specific sense. In the full electroweak theory, the symmetry is a gauge symmetry, a mathematical transformation that leaves the equations invariant but acts on the fields in a specific way. The Mexican hat potential is symmetric under this gauge transformation. It looks the same if you perform the transformation. But when the Higgs field settles into one of the minima of the Mexican hat potential, it breaks this symmetry. The specific value it chooses, a non-zero background value in a specific direction in the abstract space of the Higgs field, is not invariant under the gauge transformation. The symmetry is broken by the choice of minimum. This is spontaneous symmetry breaking of a gauge symmetry, and it is precisely what generates the masses of the W and Z bosons through the Higgs mechanism. The three-gauge bosons of the weak interaction that would be massless in the symmetric phase, two W bosons and the Z boson, acquire masses when the Higgs field breaks the symmetry by settling into its non-zero minimum. The mathematical mechanism involves the famous Goldstone theorem, which states that when a continuous symmetry is spontaneously broken, massless scalar particles, called Goldstone bosons, must appear. In the case of a global symmetry, these Goldstone bosons are physical particles. But in the case of a gauge symmetry, the Goldstone bosons are absorbed by the gauge bosons. They become the longitudinal polarization modes of the massive W and Z bosons. The gauge bosons literally eat the Goldstone bosons and become massive. This is the Higgs mechanism in its most precise formulation. The Goldstone bosons that would arise from the spontaneous breaking of the gauge symmetry are not physical particles. They are eaten by the gauge bosons, which become massive as a result. What is left over, the remaining physical degree of freedom of the Higgs field, is the Higgs boson itself, the ripple in the Higgs field around its minimum. This mathematical structure is elegant and precise. It explains why the W and Z bosons are massive while the photon remains massless. The Higgs mechanism breaks the SU2 times U1 gauge symmetry of the electroweak theory down to the U1 gauge symmetry of electromagnetism, giving mass to 3 of the 4 gauge bosons while leaving 1, the photon, massless. And it explains why the Higgs boson is special, why it is the specific particle that was predicted and discovered. It is the remnant of the symmetry breaking, the physical particle that is left over after the symmetry of the Higgs field is broken and the Goldstone bosons are eaten. It is the quantum of vibration of the Higgs field around its non-zero background value. The concept of spontaneous symmetry breaking is not unique to particle physics. It appears throughout condensed matter physics, in the theory of phase transitions, in the study of superfluids and superconductors, and it was understanding these condensed matter systems that first gave physicists the intuition to apply the mechanism to particle physics. Philip Anderson, the American condensed matter physicist whose work Higgs read in 1964, had already understood that the electromagnetic gauge symmetry could be effectively broken in superconductors, that the photon effectively acquires a mass inside a superconductor, giving rise to the Meissner effect, in which magnetic fields are expelled from the interior of a superconductor. Anderson pointed out that a similar mechanism might give mass to gauge bosons in particle physics. This connection between condensed matter physics and particle physics, between the physics of electrons in metals and the physics of fundamental particles, is one of the most beautiful instances of unification in physics. The same mathematical structure describes phenomena at completely different scales and in completely different contexts. The Higgs mechanism in particle physics and the Meissner effect in superconductivity are at a deep mathematical level the same phenomenon. This cross-fertilization between fields, the application of ideas developed in one context to problems in another, is characteristic of the most productive periods in the history of physics. The mathematical tools developed to understand phase transitions in statistical mechanics were applied to the renormalization of quantum field theories. The geometrical ideas developed by mathematicians to study curved spaces were applied by Einstein to the theory of gravity. The concept of symmetry, developed in group theory in the 19th century, became the organizing principle of the standard model of particle physics. The Higgs mechanism is part of this tradition of cross-fertilization. It was born in the intersection of condensed matter physics and particle physics, in the recognition that the same mathematical structure could explain phenomena as different as the behavior of superconductors and the masses of fundamental particles. As the final thread of this story unwinds, consider what the Higgs boson has taught us about the nature of the physical world. It has taught us that mass is not a fundamental, intrinsic property of particles. It is a relational property, a consequence of how particles interact with the Higgs field. In a universe without the Higgs field, or in a universe where the Higgs field had zero background value, the particles of the Standard Model would be massless. It is the specific, contingent fact about our universe that the Higgs field has settled into a non-zero background value of 246 gigaelectron-volts that gives the particles their masses and allows atoms, chemistry, and life to exist. It has taught us that the vacuum of space is not empty. The vacuum, the state of lowest energy, the state that the universe tends toward in the absence of any particles, contains a non-zero Higgs field. The vacuum is filled with an invisible, all-pervading field that interacts with particles as they move through it, giving them their masses. Empty space is not empty. It has structure. It has content. It is a physical medium, with properties that determine the behavior of everything that passes through it. It has taught us that the symmetries of nature can be hidden, that the laws of physics can have symmetries that the actual state of the universe does not respect. The electroweak symmetry is a symmetry of the equations, but the vacuum of our universe breaks that symmetry, hiding it behind the non-zero background of the Higgs field. The world does not look symmetric, but the laws are. The symmetry is there, it is just spontaneously broken, and it has taught us the power and the limitation of theoretical prediction. The Higgs mechanism was proposed in 1964, 50 years before its confirmation. The prediction was based on mathematical reasoning, on the requirements of consistency between quantum field theory and gauge symmetry. It was not based on any experimental observation of the Higgs boson. It was a pure theoretical prediction arising from the internal logic of the theory, and it was correct. But the theory could not predict the mass of the Higgs boson that required experiment. The theory told us that the Higgs boson had to exist, and told us how its mass would depend on the curvature of the Higgs potential, but it could not tell us what that curvature was. Only the LHC could answer that question, and when the LHC answered it, 125 gigaelectron-volts, it completed the picture. That completion is, in its way, one of the most beautiful things in science. A theory developed over decades, from the first quantum field theories of the 1920s and 1930s, through the renormalization of quantum electrodynamics in the 1940s and 1950s, to the electroweak unification of the 1960s and 1970s. A theory tested and refined and extended over a century, finally confirmed in its last missing piece by the most powerful machine ever built, the Higgs boson, the field that fills all space. The mechanism that gives mass to the particles of the universe, confirmed at last by the patience and ingenuity and collaborative effort of thousands of scientists from around the world, working together for decades toward a single question. And now, tonight, known to you, carried in your awareness through the quiet of this night. The universe is very deep, and it has been generous enough to let us see into it this far. Rest now in the knowledge that the invisible field that fills all of space is holding you, interacting with every electron in your body, giving mass to everything you are made of. That is enough. That is more than enough. The Standard Model of particle physics is built on three mathematical symmetry groups, SU3, SU2, and U1, that describe the strong, weak, and electromagnetic forces respectively. The Higgs mechanism is responsible for the spontaneous breaking of the SU2 times U1 electroweak symmetry down to U electromagnetism, giving the W and Z bosons their masses while leaving the photon massless. This mathematical structure, 3 gauge groups, 12 gauge bosons, 3 generations of quarks and leptons, plus the Higgs, is summarized in the Standard Model Lagrangian, a single mathematical expression that encodes all the dynamics of all the known fundamental particles and their interactions. The Lagrangian fits on a single t-shirt, as physicists are fond of pointing out, though reading it requires a deep knowledge of quantum field theory, gauge symmetry, and the representation theory of Lie groups. The Standard Model is, in this sense, one of the great achievements of human intellectual effort, a compact, precise, extraordinarily successful description of the fundamental constituents of matter and the forces between them. It was developed over roughly 50 years, from the first quantum field theory of the electromagnetic force in the 1940s to the confirmation of the top quark in 1995 and the Higgs boson in 2012, through the combined efforts of hundreds of theoretical and experimental physicists. And yet, as we have noted, the Standard Model is incomplete. It leaves out gravity. It does not explain dark matter or dark energy. It does not explain the matter-antimatter asymmetry. It does not explain the specific values of its own parameters, the masses of the quarks, the coupling constants, the mixing angles. These parameters must be measured experimentally. The Standard Model cannot derive them from first principles. These gaps point toward what physicists call physics beyond the Standard Model, the deeper theory that will include the Standard Model as a limiting case, while also explaining what the Standard Model cannot. The search for this deeper theory is the central program of fundamental physics today. One of the most compelling clues about what lies beyond the Standard Model is the hierarchy problem, the fine-tuning problem associated with the Higgs mass that we touched on earlier. The observed Higgs mass of 125 gigaelectron-volts is much smaller than the Planck scale, the scale at which quantum gravitational effects become important, approximately 10 to the 19th gigaelectron-volts. In the Standard Model, the Higgs mass receives large quantum corrections from virtual particles, corrections that naturally scale with the cutoff energy of the theory. For the corrections to leave the Higgs mass at 125 gigaelectron-volts, there must be an extraordinary cancellation, parts in a million trillion, between the bare Higgs mass and the quantum corrections. Most physicists find this level of fine-tuning unacceptable. It suggests that something in the theory is not understood, that there is additional physics that naturally enforces the smallness of the Higgs mass without requiring miraculous cancellations. Supersymmetry is the most studied solution. It introduces a partner particle for every Standard Model particle, with the partner's contributions to the Higgs mass exactly cancelling the partner's contributions, leaving the Higgs mass naturally small. The LHC has searched for supersymmetric particles and has not found them, at least not in the mass range it can access. This has pushed the predicted masses of supersymmetric particles to higher values, or has suggested that supersymmetry, if it exists, operates differently from the simplest models. Other solutions to the hierarchy problem, composite Higgs models, extra dimensions, relaxation mechanisms, are also being explored. The hierarchy problem remains unsolved. The LHC data have deepened the problem rather than resolving it. And the resolution, when it comes, will almost certainly require new ideas about the relationship between the Higgs field, the vacuum, and the other forces and fields of nature. The Higgs boson has one more story to tell, the story of what the universe was like before the Higgs field settled into its current value, and what might happen to the Higgs field in the far future. In the very early universe, in the first moments after the Big Bang, the temperature was so high that the thermal energy of the plasma far exceeded the energy of the Higgs field's background value. At these temperatures, the Higgs field was in a different phase, a phase in which its effective potential was dominated by thermal corrections and the minimum of the potential lay at zero. The electroweak symmetry was unbroken. The W and Z bosons were massless. Quarks and leptons moved through the plasma without mass. As the universe expanded and cooled, the temperature fell below a critical value, approximately 100 gigaelectron-volts in energy units, at which the effective Higgs potential changed shape. The minimum at zero became unstable, and the field rolled down to its current non-zero value. This is the electroweak phase transition, the moment in the history of the universe when the Higgs field acquired its background value and the particles of the Standard Model acquired their masses. The electroweak phase transition occurred approximately 10 to the negative 11 seconds after the Big Bang. 100 billionths of a second into the life of the universe. At this moment, the universe transitioned from a symmetric, massless phase to the broken symmetry, massive phase we inhabit today. The transition was a cosmological event of profound importance, the moment at which the structure of matter as we know it was established. Physicists are interested in the nature of this phase transition, whether it was a sharp first-order transition, with bubbles of the broken phase nucleating in the symmetric phase and expanding to fill the universe, or a smoother crossover. The answer has implications for the matter-antimatter asymmetry. Certain mechanisms for generating the observed excess of matter over antimatter require a strong first-order electroweak phase transition. The Standard Model predicts a smooth crossover rather than a first-order transition, which is one of the reasons why the Standard Model cannot explain the matter-antimatter asymmetry and why new physics is needed. And what about the far future? The precise value of the Higgs boson's mass, combined with the mass of the top quark, determines the stability of the Higgs vacuum. Calculations suggest that our current vacuum state, the non-zero background value of the Higgs field, may be metastable rather than absolutely stable. There may be a deeper minimum of the Higgs potential at much larger field values, which is the true ground state of the universe. If the current vacuum is metastable, it could in principle tunnel to the lower energy true vacuum through quantum mechanical processes. The timescale for such a transition is calculated to be astronomically large, far longer than the current age of the universe. The universe is, in all practical terms, stable. But the metastability of the vacuum, if confirmed, would mean that the universe is not in its true ground state, that the Higgs field is, on a cosmic timescale, resting in a local minimum rather than the global minimum of its potential. This possibility that the universe exists in a false vacuum, sustained by an enormous potential barrier, with a true vacuum that has different properties waiting beyond that barrier, is one of the more philosophically startling implications of the precise Higgs mass measurement. It suggests that the structure of the universe as we know it, atoms, chemistry, life, depends not just on the laws of physics, but on the specific history of the cosmos, on which minimum of the Higgs potential the field settled into in the early universe. If the field had settled into the true vacuum rather than the metastable one, the universe might have had entirely different properties. The electrons might have different masses. Atoms might not exist. Life as we know it might be impossible. We exist, in this picture, in a particular phase of the Higgs field, a metastable phase that happens to permit atoms and chemistry and life. The universe could have been otherwise. We are, in a very specific sense, the beneficiaries of the particular configuration that the Higgs field happened to take on in the earliest moments after the Big Bang. That is a profound thought, and it is one that connects the discovery of the Higgs boson, a particle physics measurement, to the deepest questions of cosmology and existence. Before the story rests, there is one more beautiful thing to consider. The Higgs boson is the only fundamental scalar particle in the Standard Model, the only particle with zero spin. All the other particles have spin, quarks and leptons have spin 1/2, the gauge bosons have spin 1, the graviton has spin 2. The Higgs boson, with spin 0, is unique. This uniqueness has mathematical consequences. A spin 0 particle can have a non-zero vacuum expectation value, a non-zero background value, in a way that preserves the symmetries of the vacuum. A spin 1 or spin 2 field with a non-zero background value would break Lorentz invariance. It would pick out a preferred direction or frame of reference, violating the relativity of Einstein's special theory. But a scalar field, a field with no spin, no preferred direction, can have a non-zero value everywhere in space without breaking any spatial symmetry. This is why the Higgs field, rather than some other field, is responsible for electroweak symmetry breaking. Only a scalar field can have a non-zero background value without breaking Lorentz invariance. Only a scalar field can permeate all of space uniformly, pointing in no direction, preferring no frame of reference, and yet still having a non-zero value that interacts with other particles and gives them mass. The Higgs boson is, in this sense, the most democratic of particles. It fills all of space equally, with no preferred direction, and it gives mass to all the particles that couple to it in proportion to their coupling strength, without any geometric bias. It is the background against which everything else happens, the invisible medium through which particles move and acquire mass. The universe has this background. We are immersed in it. Every atom of your body, every photon of light that reaches your eyes, every force that acts on every particle, all of it happens in the presence of the Higgs field's background value, which shapes the masses and interactions of everything. And now, having followed the story from the concept of quantum fields to the Mexican hat potential, to the LHC discovery, to the deepest implications for the structure of the universe, you can rest in the knowledge that you understand something extraordinary. You understand, at least in outline, why particles have mass. You understand the Higgs mechanism. You understand why the Higgs boson matters. And the Higgs field is there, filling the space around you, as it has been since the universe was 1/100th of a billionth of a second old, as it will be long after the last stars have burned out. Steady, patient, invisible, and utterly essential to everything. In the years since the Higgs boson was discovered, physicists have been doing something that might be called reverse engineering the universe. They have the particle, they know its mass, they can measure its couplings, and from these measurements, they are trying to reconstruct the shape of the Higgs potential, the Mexican hat landscape, whose valleys and slopes determine everything about the Higgs mechanism. The background value of the Higgs field, the position of the valleys in the Mexican hat potential, was already known before the discovery, inferred from precision measurements of the W and Z boson masses and the weak interaction. The value is 246 gigaelectron volts. The Higgs boson mass of 125 gigaelectron volts then constrains the curvature of the potential at the minimum, the sharpness of the valley walls. But there is more to the Mexican hat potential than its minimum and its curvature there. The potential has high-order terms that describe the self-coupling of the Higgs field, the interactions of multiple Higgs bosons with each other. These high-order terms determine the global shape of the potential, whether it rises smoothly away from the minimum or flattens out or develops additional features at large field values. Measuring these high-order terms requires observing processes in which 2 or 3 Higgs bosons are produced simultaneously, processes that are extremely rare and extremely difficult to measure. The high-luminosity LHC, with its much larger dataset, may be able to see the first evidence for double Higgs production and thereby constrain the Higgs self-coupling. Future circular colliders, producing millions of Higgs bosons, would measure the self-coupling more precisely. The shape of the Higgs potential is not merely a theoretical curiosity. It determines the stability of the electroweak vacuum. It determines what happened during the electroweak phase transition in the early universe. It determines whether the matter-antimatter asymmetry could have been generated at the electroweak phase transition. And it may contain clues about physics beyond the standard model. Deviations from the standard model prediction for the self-coupling could indicate that the Higgs field couples to other, undiscovered fields. In this sense, the Higgs boson is not the end of the story. It is the beginning of a new phase, the precision exploration of the Higgs sector, the mapping of the Higgs potential, the search for the deeper physics that the Higgs mechanism points toward. The discovery in 2012 answered the question, does the Higgs boson exist? The answer is yes. The questions that follow are deeper and harder. What exactly is the shape of the Higgs potential? What gives the Higgs its mass? Why is the Higgs mass so much smaller than the Planck scale? What is the connection between the Higgs field and the dark energy that fills the vacuum? Is there more than one Higgs field, or just one? These questions will occupy physicists for decades. The answers, when they come, will deepen our understanding of the invisible landscape of fields that underlies the visible universe, the landscape through which particles move, acquiring mass, interacting, forming atoms and molecules and stars and life. We are, in the end, patterns in a sea of quantum fields. Ripples in the Higgs field and the quark fields and the lepton fields and the electromagnetic field and all the other fields of the Standard Model, organized by the forces that connect them, shaped by the symmetries and their breaking, sustained by the specific values that the parameters of the universe happen to have taken. The Higgs boson is the particle that confirms this picture. It is the ripple in the field that gives mass to the ripples in the other fields. It is the quantum of the background, the excitation of the invisible medium through which everything else moves. And tonight, lying still in the dark, you are made of ripples in quantum fields, sustained by the Higgs mechanism, shaped by the laws of physics, existing in a universe that has the precise structure it has because of a field that settled into a non-zero background value 1/100th of a billionth of a second after the Big Bang. That is an extraordinary way to exist, and it is worth knowing as you drift towards sleep that you know it. The Higgs field is there, invisible and real, filling the space around you, giving mass to every particle in your body, patient and pervasive and ancient. And the universe, having taken the shape it has, is the kind of place where something as remarkable as a conscious being can lie down in the dark and think about quantum fields. That is extraordinary. And it is enough. Rest now. The Higgs field will keep. The Mexican hat potential will keep. The LHC will keep collecting data and measuring couplings and searching for deviations. And you can sleep. The universe is deep and it is lawful and it is full of fields. And for now, that is everything. The relationship between the Higgs boson and the other particles of the Standard Model reveals a striking pattern. The heavier the particle, the more strongly it couples to the Higgs field, and therefore the more mass it acquires. The top quark, the heaviest elementary particle in the Standard Model, has a Yukawa coupling to the Higgs field of approximately 1, the largest coupling of any known particle. This coupling is not just large, it is close to unity, which has led some physicists to wonder whether the top quark mass and the Higgs mechanism are connected in a deeper way than the Standard Model reveals. The top quark mass is approximately 173 gigaelectron-volts, comparable to the Higgs background value of 246 gigaelectron-volts. This rough coincidence of scales may be accidental, or it may be a clue about the structure of the Higgs sector beyond the minimal Standard Model. The bottom quark, the next heaviest quark, has a coupling to the Higgs of about 0.2. The charm quark couples at about 0.7. The strange down and up quarks couple at progressively smaller values. The electron couples at about 0.3, an extraordinarily small coupling that gives the electron its small mass. The muon couples at about 0.6, 600 times the electron's coupling, which is why the muon is about 200 times heavier than the electron. This hierarchy of couplings, spanning 6 orders of magnitude from the top quark to the electron, is one of the deepest puzzles in particle physics. Why does the top quark couple to the Higgs so much more strongly than the electron? The Standard Model describes these couplings as free parameters. They must be measured experimentally, not derived from theory. But the vast range of values, from order 1 for the top to order 10 to the -6 for the lightest quarks, suggests that there is a deeper structure, a more fundamental explanation for why the particles have the masses they do. This is called the flavor problem or the fermion mass problem. It is one of the great unsolved problems in particle physics. Understanding why the particles of the Standard Model have the masses they do, why the electron is so light, why the top quark is so heavy, why the 3 generations of quarks and leptons have such different masses, requires going beyond the Standard Model and finding the deeper theory that explains the Yukawa couplings rather than just parameterizing them. Some approaches to this problem invoke extra dimensions, the idea that the different generations of quarks and leptons are actually a single particle propagating in extra spatial dimensions, with the apparent mass hierarchy arising from different profiles of the particle's wave function in the extra dimensions. Others invoke flavor symmetries, additional symmetries that constrain the structure of the Yukawa couplings and explain the hierarchies through the mathematics of symmetry breaking. Still others invoke the existence of additional Higgs fields, multiple Higgs doublets, each coupling to different sets of particles. None of these explanations has yet been confirmed. The fermion mass problem remains open. And the Higgs boson, by precisely measuring the couplings of the standard model Higgs to the known particles, may provide clues. If the measured couplings deviate from the standard model predictions, if they do not scale precisely as the fermion masses, it would suggest that the Higgs sector is more complex than the minimal standard model predicts. The study of the Higgs boson is thus not merely the completion of the standard model. It is the opening of a new window onto the deeper structure of matter, a window through which the next generation of discoveries may appear. One of the most beautiful aspects of the Higgs story is the way it exemplifies the relationship between mathematics and physical reality. The Higgs mechanism was not discovered experimentally. It was invented mathematically, constructed as a solution to a theoretical problem, without any experimental guidance beyond the known masses of the W and Z bosons and the structure of the electroweak theory. The physicists who proposed the Higgs mechanism in 1964 were solving an equation. They were not looking at detector data and wondering what new particle might explain an anomaly. They were following the internal logic of a mathematical theory, gauge field theory, and asking what it required. The theory required a mechanism for giving mass to the gauge bosons without destroying the gauge symmetry. The only consistent mechanism was spontaneous symmetry breaking through a scalar field with a non-zero background value. And that mechanism predicted a new scalar particle, the Higgs boson. This is the scientific method at its most abstract and most powerful. Not experiment guiding theory, but theory constraining experiment, the mathematics of gauge symmetry telling physicists what must exist, and experiment confirming it half a century later. The same pattern has appeared throughout the history of modern physics. Dirac's equation predicted the existence of the positron, the antiparticle of the electron, before it was discovered experimentally. The mathematical structure of the equation demanded a second solution with positive energy and opposite charge. Anderson discovered the positron in cosmic ray tracks 2 years after Dirac's prediction. Einstein's general relativity predicted gravitational waves, ripples in the fabric of spacetime, nearly a century before LIGO detected them in 2015. The mathematics was so precise and so compelling that physicists were confident the waves existed long before they could be measured. The Higgs boson fits this tradition. The mathematics of gauge field theory, combined with the requirement that the W and Z bosons be massive, demanded a scalar field with a non-zero background value and predicted its quantum excitation. The prediction was confirmed 50 years later by the most powerful machine ever built. This is what makes physics extraordinary. The universe is mathematically consistent, and it is consistent in ways that allow us to predict its content from its structure. We can discover particles in the equations before we discover them in the detectors. The universe is, in this sense, legible, written in a mathematical language that human minds can learn to read. The Higgs boson was there in the equations long before it was there in the data. The field was filling all of space with its non-zero background value long before anyone knew to look for it. The mechanism was giving mass to the W and Z bosons, had been doing so since 10 picoseconds after the Big Bang, long before any human being understood why those particles were heavy. The universe does not wait for us to understand it. It simply is what it is, operating by its own mathematics, generating its own structure. We are latecomers to the story, arriving billions of years after the Higgs field settled into its current value and finding, with the tools of mathematics and experiment, the evidence of what happened. The Higgs boson is that evidence, the field that fills all space, the mechanism that gives mass, the prediction confirmed, the mathematics made real. Rest in that tonight. The equations were right. The field is there, and you, made of particles that owe their masses to that field, are here to know it. That is the Higgs story, and it is one of the most beautiful in physics. As we come to the end of our journey tonight, the story can begin to settle around you. We have traveled from the concept of quantum fields and particles as ripples, through the mathematics of potentials and resting values, through the Mexican hat potential that forces the Higgs field to settle into a non-zero background, through the mechanism by which this background gives mass to otherwise massless particles, through the history of the 1964 papers that first proposed the mechanism, through the decades of searching and the construction of the Large Hadron Collider, to the moment of discovery on July 4, 2012, when the signal appeared in the data and 50 years of theoretical prediction were confirmed. There is no need to hold any of that tightly now. You can let the details soften into impressions. The image of a field that fills all of space with a constant background value, invisible but real, interacting with every massive particle as it moves through space. The image of the Mexican hat potential, the mathematical shape whose valleys, lying away from the origin, force the field into a non-zero resting state. The image of a 27-kilometer ring of superconducting magnets buried underground near Geneva, accelerating protons to nearly the speed of light and colliding them in search of a particle that gives other particles their mass. The image of Peter Higgs, 83 years old, sitting in an auditorium and weeping. Let these images drift through your awareness and dissolve, like starlight through dark water. The Higgs field is there right now, filling the space around you, filling the space of the room, filling the space inside your body, passing through every atom, interacting with every electron, giving every electron its mass. You have been in the Higgs field your entire life. You could not exist without it. That is an extraordinary thing to know, and knowing it, you can rest. Let your breathing slow. Let your body settle into wherever it is. The universe will keep unfolding on its own, just as it always has, steady, patient, and kind. Sleep well, good night, still drifting. Let the rain take over from here. Close your eyes and let it wash everything away.